Hello everyone, this is Chinnaiah Kalpana here. In this video, we're going to see a problem from Legender's equation. So let's get going. Problem: solve x plus a whole square into d square minus 4 times x plus a into d plus 6 into y equal to x. So we are given a differential equation of the form ax plus b whole square. Right, we'll write in terms of n. Order n, okay? D power n by dx power n plus p1 into ax plus b power n minus 1 into d power n minus 1 y by dx power n minus 1 plus so on plus p and y equal to some function of x. It's the Legender's equation. The given equation is of this form, so we call it as Legender's equation. Now we'll solve this equation by reducing it to linear equation with constant coefficients by making some substitutions. Okay, now coming to the problem. Given differential equation x plus a whole square into d square minus 4 times x plus a into d plus 6 into y equal to x. Consider as equation number 1. We know that from Legender's method, ax plus b equal to e power z, that is ax plus b can be replaced by e power z, then z becomes log of ax plus b, and theta is a differential operator whose independent variable is z, and ax plus b into d can be replaced by coefficient of x a into theta, since we are having power 1, and ax plus b whole square into d square. Here I am having square, right? So you can replace this by a square into, since you are having power 2, right? So you'll get two terms, theta into theta minus 1. Likewise, if you have 3, you'll get a cube into theta cube, theta into theta minus 1 into theta minus 2. Okay, well, now coming to our problem, let x plus a equal to e power z, then z equal to log of x plus a. Here we'll use the differential operator theta, whose variable is z, whose independent variable is z, and here x plus a into d can be replaced by, see here a is a constant, okay, and we can replace it by coefficient of x is 1, so 1 into theta is theta, and x square plus a square into d square, x plus a whole square into d square can be replaced by coefficient of x is 1 square is 1 into, since we are having square, so you'll get two terms, theta into theta minus 1. Now the above equation becomes, we'll just make the substitution here, right? Then 1 becomes, replace x plus a whole square into d square by theta of theta minus 1, minus 4 into replace x plus a into d by theta, plus 6 into y equal to, you're having x, right? Since we have x plus a equal to e power z, from this we'll find x. By taking this a to RHS, we'll get e power z minus a, then x can be replaced by e power z minus a, right? The RHS part becomes e power z minus a. This becomes theta into theta square minus theta into 1 theta minus 4 theta plus 6 into y equal to e power z minus a, right? Or theta square minus theta minus 4 theta gives us minus 5 theta plus 6 into y equal to e power z minus a. Consider as equation number 2, which is of the form, which is in operator form, say f of theta into y equal to some function of z. Okay, f of theta into y equal to RHS part, which is in z, in terms of z otherwise, where f of theta is theta square minus 5 theta plus 6 and R is e power z minus a. It's 2, okay? Fine. Now, we'll find the solution to this equation 2 using, the general solution using y equal to yc plus yp, where yc is complementary function, yp is particular integral. We'll find yc using auxiliary equation, and we'll find yp using 1 by f of theta into the RHS part of the reduced equation. Okay, fine. See, we have reduced the given differential equation, that is Legender's equation, to a linear equation with constant coefficients, right? A linear equation with constant coefficients, we can say. And now we are going to find the general solution to this equation 2 using y equal to yc plus yp, which comes in terms of z, okay? And later, using the solution or the general solution of 2, we'll find the general solution of the given differential equation or equation 1, which comes in terms of x. Okay, so let's see. Now coming to auxiliary equation. The auxiliary equation is f of m equal to 0, where f of m equal to, we have f of theta square minus 5 theta plus 6, right? Then just replace theta by m in f of theta, so that you'll get f of m equal to m square minus 5m plus 6. Now the auxiliary equation becomes m square minus 5m plus 6 equal to 0. Now we need to find roots to this equation. Let's split minus 5m as minus 2m minus 3m. Now take m common from the first two terms and take minus 3 common from the next two terms. Now take m minus 2 common from these two terms, we'll get m minus 2 times m minus 3 equal to 0. Now equate each factor to 0. M minus 2 equal to 0, m minus 3 equal to 0. This gives us m equal to 2, m equal to 3. Right? Then m equal to 2, 3 are the roots to this equation, auxiliary equation, we can see. So the roots are real and distinct. We know that when two roots, say m1 and m2, are real and distinct, then the complementary function will be one constant into e power one root into variable plus another constant into e power another root into variable. See, the equation 2 is in terms of theta and z, right? Theta is nothing but derivative with respect to, it's a differential operator whose independent variable is z, right? So here we'll take z because we are finding yc to this equation 2, right? So here we'll consider the variable z, not x. Fine. Now coming to our complementary function. So here the roots are 2 and 3. Let's write our complementary function. One constant into e power one root, say 2 into z plus another constant into e power another root into z, which gives us c1 e power 2z plus c2 e power 3z. Therefore, yc equal to c1 e power 2z plus c2 e power 3z. Now we got yc, let's now find yp. So we can write yc as also as c1 e power 2z can be written as e power z whole square plus c2 e power 3z can be written as e power z whole cube. In order to replace e power z by x plus a, we can just write e power 2z as e power z whole square. Okay, we'll use this later. Now coming to yp. Yp is given by 1 by f of theta into RHS part of the reduced equation, equation 2. We have f of theta square minus 5 theta plus 6 and r is e power z minus a. right? We can write this as 1 by theta square minus 5 theta plus 6 into e power z minus 1 by theta square minus 5 theta plus 6 into a, right? So here we'll write this a as a into 1, since we know that 1 is e power 0, right? And we can write e power 0 as e power 0 into z, right? Since 0 into z is 0 again. So you'll get a can be written as a into e power 0 z. In the next step, we'll write this a as a into e power 0 z. Right? Fine. So let's find these two separately for our convenience. We have f of theta equal to theta square minus 5 theta plus 6, right? See, this is of 1 by f of theta into e power bz type or e power az. Okay, now we'll find f of a, that is f of, just compare az is e power z with e power az. Then for a equal to 1, we'll find f of 1. Just replace theta by 1 in f of theta, then you'll get f of 1 equal to 1 square minus 5 into 1 plus 6, which gives us 1 minus 5 plus 6. 1 plus 6 is 7 minus 5, which is 2. Non-zero. Since f of 1 is non-zero, so you can replace theta by 1 in the first term. Okay, now coming to the second term. So here also we have f of theta equal to theta square minus 5 theta plus 6, right? So this is also of, you need to write one more step here. Since a is constant, so we'll write the second term as a into 1 by theta square minus 5 theta plus 6 into e power 0 z. Okay, here 1 by theta square minus 5 theta plus 6 into e power 0 z is of the form 1 by f of theta into e power a z type. Okay, now just compare e power 0 z with e power a z. Then for a equal to 0, we'll find f of a, that is f of 0, which is equal to, just replace theta by 0, you'll get 0 minus 5 into 0 plus 6, which gives us 6, which is again non-zero. Since f of 0 is non-zero, so you can replace theta by 0 in the denominator. Okay, then this becomes, since f of 1 is non-zero, since f of 0 is non-zero, then we'll just replace the theta. Then yp becomes 1 by, replace theta by 1, you'll get 1 square 1 minus 5 into 1 plus 6 into e power z minus a into 1 by, since f of 0 is non-zero, so just replace theta by 0, you'll get 0 square 0 minus 5 into 0 plus 6 into e power 0 z. This gives us 1 by 1 minus 5 plus 6 into e power z minus a into 1 by 0 minus 0 plus 6 into e power 0 z. This equals to 1 by 7 minus 5 into e power z minus a into 1 by 6 into e power 0 z is e power 0. This is equals to 1 by 2 into e power z minus a by 6 into, since e power 0 equal to 1, so we'll get 1 by 6 into 1, which is a by 6. This gives us e power z by 2 minus a by 6. Therefore, yp equal to e power z by 2 minus a by 6. So we got yp and yc. So let's now write the general solution to equation 2, which is given by y equal to yc plus yb. Therefore, the general solution to equation 2 is given by y equal to yc plus yp, then y equal to yc c1 e power 2z plus c2 e power 3z plus yp is e power z by 2 minus a by 6. See, the solution is in terms of z, which is general solution to the reduced equation, equation 2. Okay. Now, we'll find the general solution to the given differential equation, that is equation 1. Using this solution, we have yc equal to c1 e power 2z plus c2 e power 3z plus e power z by 2 minus a by 6, right? We'll just write e power 2z as e power z whole square plus c2 into write e power 3z as e power z whole cube plus e power z by 2 minus a by 6. Since e power z equal to x plus a, then this equation becomes y equal to c1 x plus a whole square plus c2 x plus a whole cube plus e power z, that is x plus a by 2 minus a by 6, which is a required solution, that is the general solution to the given differential equation. So this is general solution to the reduced equation, that is the equation in terms of theta and z, and this is the general solution to the given differential equation. Therefore, the general solution to equation 1 is y equal to c1 into x plus a whole square plus c2 into x plus a whole cube plus x plus a by 2 minus a by 6. Well, we have seen a problem from Legender's equation in this video. I hope you'll understand. We'll see you in the next video. Until then, bye bye.